It is section 4.5, Gaussian quadrature. We first recall Newton-Cotes formulas in section 4.3. There, we studied how to create quadrature formulas of this form. These formulas are exact for polynomials of degree n, and that is true if and only if the weights are chosen from the integral of Lagrange cardinal functions. In those formulas, the choice of knots x0 to xn were made a priori. Once the knots were fixed, then the weights were determined uniquely from the requirement that the formula must be equal for polynomials of degree Pn. Okay, that is recalled. Now we'll begin here the method of undetermined coefficients. Let's see this example. Find W0, W1, W2, the weights with which the following formula is exact for all polynomials of degree 2. And in this formula, the integral is from 0 to 1. The evaluation points are here 0, half, and 1. The 3 points, x0, x1, x2 are already given. Now we try to decide W0, W1, W2 such that this formula is exact for quadratic polynomials. So we may try to use trial functions f of x is 1, x, and x squared. Then for each of these trial functions, here integral of 1, f is 1 here now, then we know that the true value is 1 and right side must be given in this way. F has always the value 1, so we have that one. So we rewrite here. Now f is x, then the integral will be half, and x, the function x at 0 must be 0, at half the value must be half, and at 1 the value must be 1. So we reshare these terms. For x squared, the integral is 1/3, and again here at 0 must be 0, the f0 must be 0, f half must be half squared, because in this case f is x squared, and at 1 the value must be 1. So we have that. We have 3 equations and 3 unknowns and linearly combined. So we have the linear system of 3 variables, 3 unknowns. We can solve it quite easily. Once you solve, then you can get here W0, W1, W2 are 1/6 and 2/3 and 1/6. So we can finish the formula here by using here. We can write here. Okay, this is exact for quadratic polynomials. Okay. Now here it must be noticed that this formula is the elementary Simpson's rule with h is 1/2. Here now 6th contribution, and that is 2h. Originally in elementary Simpson's rule, this position, it is 2h, which is now 1, and here 1 for 1 contribution divided by 6, so it is a kind of average height. Okay. Now here we start with Gaussian quadrature. The idea of Gaussian quadrature is choose knots in an optimal way. Once the knots are chosen, then weights must be determined uniquely, and that is a standard way we can decide the weights. The question is how to choose knots, and Gaussian quadrature will choose the knots in an optimal way rather than using equally spaced points. The knots x1 to xn in the interval and the weight w1 to wn are chosen to minimize the expected error in this formula. Now, to measure the accuracy, we assume that the best choice of these values produces the exact result for largest class of polynomials. So we try to limit our analysis in polynomial spaces so that we try to get the knots and weights so that it is exact for the largest the class of polynomials. Okay. Then here we have two unknowns, 2n parameters, x1 to xn and w1 to wn, so that in polynomial space the choice is now 2n minus 1 degree of a polynomial, because it can be decided along with 2n parameters. Okay, let's see here example. Determine x1, x2, w1, w2 so that the integration formula gives exact result whenever f is chosen from cubic polynomial space. Okay. As in the previous example, we try to use a method of undetermined coefficients. In this case, we use f is 1, x squared, x cubed as trial functions. Let's do it. Okay, yeah. Once f is 1, then integral minus 1 to 1 dx, that must be here 2, and that is same as now right side, and w1 and f at x1 must be 1, and plus w2 and f at x2 must be again 1, because the function is always 1, right? Okay, yeah. Now if we choose f is x, then integral x from minus 1 to 1 x dx. Now this is odd function in symmetric interval, so that it must be 0. And then now this is w1 at x1, that must be x1, and plus w2 at x2. Right? Okay. How about f is x squared? Then integral from minus 1 to 1 of x squared must be here, and 2/3 you can get it quite easily. That is from minus 1 to 1 x squared dx. Okay, that is same as now w1, f at x1 is x1 squared, plus w2, f at x2 must be x2 squared. Okay, we need one more. Now f is here x cubed. Then here again x cubed is an odd function, minus 1 to 1 x cubed, an odd function with the symmetric interval, so the integral must be 0. And the right side, that is w1 and x1 cubed plus w2 and x2 cubed. So we have 4 equations for 4 unknowns. This is nonlinear, so that in general, for nonlinear system, the uniqueness of solution is not guaranteed. But for this problem, now the values are real, and we exclude complex valued solutions. And also, if we try to use symmetry, then we can find a unique solution. Yeah. Okay. Here now, the interval is now -1 to 1. We are trying to choose x1 and x2, and the corresponding weights w1 and w2. It doesn't have to be non-symmetric. There's no reason to be non-symmetric. They must be symmetric. That means that w1 must be same as w2, and okay, if we are using symmetry for simplicity, then w1 must be w2, and x2 must be minus x1, so that midpoint is 0, and x1 is given over there, the x2 is given with the reflection. Okay, if we are using this symmetry, then we can solve the problem very easily. Okay, here w1 plus w2 is 2. That means that w1 is w2 1. Each one is 1. And here, once we decide w1 and w2, then of course over there x2 must be minus x1. Okay. Now, from this one, the third equation here, there's 1, so that x1 squared plus x2 squared, which is same as now here, okay, 2 over x2 squared, that is 2 over 3 over there. So we can get x2 squared as 1 over 3. Okay, here, so that x is same as x2 is same as plus minus 1 over square root 2 over 3. So we can choose here, from here, for example, x1 is the left point, so the x1 is minus 1 over square root over 3, and x2 is now 1 over square root over 3. Along with this value, if we make the quadrature formula, then this formula must be exact for cubic polynomials, because we made it for every of these trial functions. We try to find the points and weights along with equality, so that it must be exact for cubic polynomial. So these are the answer. Okay. The method of undetermined coefficients is a classical method to determine the knots and weights for formulas, but an alternative method can obtain them more easily. The alternative is related to Legendre orthogonal polynomials. Later in this section, we'll define also what orthogonal polynomials are, and also we'll define the Legendre polynomials. We earlier studied Chebyshev polynomials. These polynomials are also orthogonal polynomials. And frequently cited classical orthogonal polynomials are Jacobi polynomials, Laguerre polynomials, Chebyshev polynomials, and Legendre polynomials. Okay, we'll continue in the second part. Thank you.